Thank you. So in this talk, I'm going to introduce ensemble-based coupled hydrology and landslide warning system. And I'm also going to show one case study. So as you can see from these figures, the top figures shows the reported flash flood events from 2006 to 2013. You can see a large portion of the United States has been impacted by the flash flood. And the lower graph shows the risk maps of the landslides across the United States. So these two figures shows flash flood and landslide are two major nature hazards in the United States. So that's very important to develop the warning system to predict the occurrence of these two hazards. And these two hazards are collected in some way because most of landslide events are triggered by heavy rainfall events, and floods are also triggered by heavy rainfall events. So it's very natural to collect these two hazards. So in this research, there are two objectives. First, we want to cap the hydrological processes with the soil mechanics to predict floods and rainfall triggered landslides. Then we want to build an ensemble-based coupled system to do this prediction. Finally, we want to evaluate this system before we can put this for operation. So here's the methodology. So since it's ensemble-based, we need multiple models. So first, we developed ensemble-based hydrological model. So the hydrological process basically can be divided into two components. First is the water balance component, which can use to generate the runoff and separate the runoff. The second component is a routing component, which basically is to calculate how water moves to the river channel. So in the water balance component, we use two models. One model is the variable infiltration curve based model. This is originally developed by the Zhang model developed in China. This model is also implemented in the CREST model developed by University of Oklahoma in 2011. And we also used another model. It's called the Sacramento soil moisture accounting model. This is a quite old model, but it has a very nice conceptual, which we adopted this is water balance component. Then we use the cell-by-cell linear reservoir routing scheme to couple with both CREST model and Sacramento model to build a whole hydrological model. Then we couple these two hydrological models with two additional landslide models. One is the trigger model developed by USGS. The other one is the slide model developed by University of Oklahoma. So the basic ideas is use the remote sensing-based forcing data such as rainfall, geography, geology, land cover, and so on, feed this into the ensemble coupled hydrology and landslide modeling system. Then we can predict the flood events and also the landslide events. So in this study, to evaluate this system, we choose one case study, the Hurricane E1, which happened in September 2004. So this hurricane was originally formed in the eastern Atlantic Ocean, just west to the African continent, and moved to the west across the Caribbean Sea, the Gulf of Mexico, and hit the mainland of the United States. Then moved north. So one of these states in the United States has been heavily impacted by this event, including the North Carolina. So in this study, we choose the Macon County of North Carolina as our study area. It's because the Hurricane Ivan caused a large impact in this area. For example, it caused about 33 landslides within 2 days and killed 8 people, destroyed 16 homes, and also caused a lot of property damage. So this shows the Macon County, the Little Tennessee River Basin. So we use this frozen data, including the stage 4 quantitative precipitation estimates, which is multi-sensor-based precipitation estimate products. And we also use other DEM data, soil data, land cover, and also the USGS stream flow data to validate our hydrological processes. So this graph shows the spatial patterns of cumulated rainfall during the 2 days carried by the Hurricane Ivan. As you can see, across this basin, most of regions received a lot of precipitation. Some regions received more than 150 millimeter precipitation within 48 hours. And this symbol shows the USGS station, river station, which is close to the outlet of this basin. This graph shows the simulated hydrograph by 2 hydrologic models, the CREST model and the Sacramento model. And the black curves shows the observed stream, observed hydrograph. As you can see, both hydrological models are capable captures the major processes of the hydrological processes. And also, this shows the spatial patterns of the runoff. The first 2 graphs shows the runoff in the beginning of the Hurricane Ivan event, which is about 5 a.m. on September 16th. You can see most of these regions has quite dry, and the river system has very low discharge. However, once the Hurricane Ivan reaches these regions, it dumped more than 100 millimeter water on the top of the on the surface, which caused large increases in river discharges, as you can see from these 2 graphs. So another response is the infiltration, which is important for the landslide events, because landslide is heavily impacted by the soil moisture and also impacted by the rainfall intensity, the cumulative rainfall intensity. So as you can see from these 2 graphs, you can find there shows some difference in these 2 hydrological models. So for example, the CREST model shows more infiltration rates than the Sacramento model. So these differences are critical for the landslide prediction, because landslide model are quite sensitive to the cumulated infiltration rate. So again, so this shows the accumulated infiltration across this whole basin by 2 models. As you can see, so the CREST model is kind of predicted more infiltration than the Sacramento model. To respond to this rainfall event and these hydrological processes, we use this ensemble system to predict the occurrence of the landslide. So the top graph shows the predicted landslide events by the CREST integrated or coupled CREST slide model, and also the coupled CREST trigger model. So you can see there are some slightly differences, but mostly these 2 models shows very consistent results. And the lower panel shows the results from the integrated SAC trigger model, SAC slide model, and the SAC trigger model. So when you compare the lower panel to the top panel, you can find actually the top panel shows more predicted landslide events. So this is because the CREST model predicted more infiltration rates than the SAC model, as you can remember from the results of the previous slide. So this does shows the sensitivity of the landslide models to the hydrological processes. And also, so because we don't have evaluation data to check how much infiltration data, so this is very important. This is the point why we want to build this ensemble system, because we want to quantify the uncertainty and do our best to present these processes in better way. Okay, to evaluate the prediction results, So usually the common ways to calculate the tree positive ratio and the tree negative ratios. And when you plot the tree negative ratios on the x-axis and the true positive ratios on the y-axis, so you can build this called a receiver operating characteristic curve. So for a perfect model, you true positive ratios should be equal to 1, which means you capture all positive events, and you also true negative ratios should be also close to 1. As well also the landslide in the most of the landslide models, when we predict the occurrence of landslide, basically is determined by the factor of safety. So once factor of safety is lower than 1, we regard it a landslide event. However, we can change risk threshold, then we can calculate different true negative and true positive ratios, then we can make a risk curve. So basically, for a perfect model, we want to the curve as close as to this point, this 1 point. So the point here, we want to show our coupled systems generally has a better results than this uncoupled trigger model, the landslide model. So this is the slide model family. And we also compare this across the trigger model family. You can also show the coupled models shows a little bit better results than this uncoupled landslide model. So as you can see, these 4 model members show the different results. Once we combine these results together, for example, we can calculate the probability of landslide occurrence. So as you can see from this graph, we can see this shows the probability of landslide events and also this observed landslide. So if we regard the probability once is larger or equal to 50%, then we can regard this landslide is going to happen. So then we can calculate the true positive and true negative ratios. As you can see, these ensemble results can largely improve the true positive ratios. So don't be scared by these low numbers of true positive ratios in the other 4 models. This is because right now our model is running quite coarse resolutions, which is about 250 meters. And actually, the landslide happens in very much lower spatial scales, like a couple meters, even up to like 30 meters. So there's a reason called relatively low true positive ratios. Okay, to conclude, so we coupled this hydrological model with the landslide model, which shows improved results. Once we build this ensemble results, which shows a further improvement, but we still found that there's a lot of room to improve our system. Thank you. So I think I have our time for maybe 1 question. Yes. Sure.
So, you said there's room for improvement. So,
yeah.
What are the next steps in trying to improve the positive rate?
Yes. So first thing, we want to increase the spatial resolution. Yeah. By doing that, we also can improve maybe the surface characteristics like slope and some other soil texture information. Yeah. Thank you.